Hello, everyone. My name is Devendra Kapadia, and I'm the manager of calculus and algebra at Wolfram. And it's a great pleasure to talk to you about what's new in calculus and algebra today. So we are part of the very traditional area of Mathematica, calculus and algebra. And of course, we've always been popular, but I'm happy to report that, in fact, thanks to the work of our excellent team, we have lots of new features which are being put into version 12.2, which is just about to come up now. So I'm going to give you a broad overview of this functionality, no technical details, just a little bit of overview and some simple examples. So let me begin by giving you an overview of the talk. So in this talk, I'd like to discuss the following areas. So we have the new function properties, which is kind of a lead feature for 12.2. Given a function, can you show it's injective, surjective, bijective, etc. Then we have special functions under which we have improved elliptic functions. We have the new Lamé functions and the holonomic functions. And then under calculus, we have greatly improved Laplace and inverse Laplace transform functionality. We have lots of improvements for ordinary and partial differential equations with dsolve. And we have asymptotic statistics for the first time, just a little bit of asymptotics and statistics combined to show the power of our system, both for asymptotics and statistics. And then from there on, I'll talk about a little bit about equation solving. Solve now is assumption. That's a very important thing for everyone to know. And then in the very last part, I'll move on to documentation, how things are being moved in that area, how we are trying to make things more useful for everyone, and the new courses, current and planned. And so hopefully all that together will give you a good picture of where we're heading in the next year or so. And of course, at the end of the talk, I'll also tell you what else we have today on the plate for you to go and enjoy. So let me begin with function properties. So when you first learn functions at middle school or wherever, you think of a function as being defined from a set A to a set B, in this case, a surjective function, and it's purely set theoretical. So you got two ovals, nothing more. And so you can talk about set theoretical properties like bijective, injective, surjective, etc. But then a little later, you go to 9th or 10th grade, and then you say, oh, that first set on the left was actually the x-axis, and second set was the y-axis. And on the y-axis and x-axis, you actually can talk about topology. You've got a notion of continuity. You have calculus to do analyticity, and you have an order, so you can talk about positive, negative, etc. So that explains our function properties function. So we have the set theoretical properties. We have new functions, function injective, function surjective, and function bijective, which will do that for you. And then we have the topological and analytic properties. And over there we have things like function discontinuities. We have function singularities, very useful to actually find the singularities and discontinuities of functions, functionality and analytic, and then you got function meromorphic. So those are slightly more advanced, but still useful to quite a lot of people. And finally, we have the sign properties. So you can ask, is the function positive? Is the function negative? Is it monotonic? Is it convex? So together, you can take your favorite function, give it to system, and it'll go ahead and do a great job of telling you exactly what the function has in terms of properties. So just to give an example, which you might even find in a standard calculus analysis textbook. So here's a function, h of x. It is continuous because at 0, where the only problem is, you can actually, let's say, put 1 over x equal to t, and then notice that sign is just oscillating between -1 and 1. So this function certainly is continuous because function continuous says that. On the other hand, the first derivative h prime is not continuous. So you've got a function with a discontinuous first derivative, and hence it is not analytic. So we can then go ahead and visualize the function in its first derivative. There you are. Okay, so clearly the function itself is quite nice, but the derivative is terribly badly behaved near the origin. So that's the key to understanding the function, that you don't have analyticity. Okay, on to the next function, which I think is worth knowing about. Function singularity is a very powerful function. It can compute the singularities of literally any function that you want, real or complex. So just a simple function, arctangent of p square. And what you see over here is that this function has actually nothing on the real axis talk about. There are no singularities. Function singularity says false. So there are no singularities at all. And if you plot it, it looks nice and smooth. So that's a really boring function on the real axis. But then as soon as you move to the complex domain, things change dramatically and you get lots and lots of singularities. So here you are, that's the function singularity result. It's huge. So you say, okay, reduce, can you help me please? And it does. And what you see over here is that, in fact, in this beautiful picture, which I showed on the cover slide, the title slide for today, you stay off the real axis, you stay outside a circle, but then along these four lines over here, you actually, for these four rays, you actually have the singularities. So function singularity is a wonderful way to figure out what exactly the singularities of your function are, and I'm sure it's going to be used widely both inside a system and outside. Okay, so now having understood what singularities are and why they're so important and why real versus complex is so important, I can then talk about elliptic functions. So we have always had these elliptic function system. In fact, the particular variety I'm talking about are called Jacobian elliptic functions, and there are 12 of them. There's JacobiZN, JacobiZN, etc. And then, of course, there are 12 inverses. So together, you have 24 of these functions. And the question is, why are there 12 of them? What does the Sn mean? Does it look like sine? That looks like cosine. How are they related, etc.? So let's see how all that relates to what we know. Okay, so on the real line, in fact, these functions are periodic and analytic. So here's Jacobi Sn of x, 1/3. And in fact, if I replace the 1/3 by a 0, then it would be exactly the sine function. So these elliptic functions are very closely related to the trigonometric functions. And in fact, they're used to describe oscillations, nonlinear oscillations. Now, when you go to the complex plane, then things change dramatically. So here is the same set of functions, but now you have a complete different behavior, because what happens is that these Jacobi functions are actually quotients of what are called theta functions, theta 1, theta 2, theta 3, theta 4. And because there are 4 functions, you can divide them in different ways. So 4p2 is 12. So there are 12 Jacobi elliptic functions. Now these theta functions are, first of all, they are analytic. And secondly, they are quasi doubly periodic. So they are almost doubly periodic, but not quite. But when you divide them, the bad things go away and you get this double periodic behavior for the elliptic function, the complex plane. So you get this beautiful tiling of the plane. And the question is, why are the holes over there? Well, that's because you're dividing by theta functions. So the singularities come from the zeros of the denominator theta functions. So that's a quick introduction to elliptic functions. And the question is, why am I talking about them now in 12.2? We had them forever. Well, in 12.2, what we've done is to make dramatic improvements for the performance of these functions. So we did that, and then the developer for geographics came and told us that, in fact, these improvements have speeded up a certain example in geographics for a particular geoprojection, PS Concula. And basically, this has become something like 35 times faster in 12.2, because underneath the hood, it's calling JacobiZN. So that's a dramatic improvement for us. We are really happy to see this happening. Okay, so you make an improvement in one part system and it goes and affects some other part. Okay, so that's the Jacobi elliptic function and why they are important 12.2. But when you do calculus with them, in fact, you have a layer on top, and we have added 2 functions to that layer on top for doing calculus. There are 2 new functions, Jacobi Epsilon and JacobiZN. So Jacobi Epsilon is actually defined to be the integral of the square of Jacobi dn. And the question is, why is it important? Well, this is a canonical form for elliptic integrals of the second kind. So when you do elliptic integral, there are 3 kinds. There's elliptic integral type 1, type 2, and type 3. And the second type can now be described very efficiently using these Jacobi epsilon function. So we're kind of making a breakthrough in a small way towards a deeper understanding of elliptic integrals in Mathematica. Now, on the other hand, we have this JacobiZN that requires a bit of explanation. So we already had Jacobi zeta, which is useful for working with elliptic functions. But the problem with Jacobi zeta is that it works with what's called the U coordinate. Now, when you work with elliptic function, you use U coordinates or phi coordinates. And Jacobi zeta was using the phi coordinates. That is not so good. It's periodic, but it has branch cuts. So in 1997, a user wrote to us saying that that's not good. You need a function that works with U and not phi. And he said that, in fact, if Carl Gustav Jacobi had been alive, he would have turned in his grave at the thought of you were doing the wrong thing. Well, 23 years later, we have fixed that problem, and we now have JacobiZN, which is actually a meromorphic extension of Jacobi zeta. So we have Jacobi zeta, which is old, and JacobiZN, which is new, but they serve slightly different purposes. So that's one way to use these Jacobi functions to do calculus. The question is, what else can you do with them? Well, what you can do with them now is to define new functions. And those are the Lamé functions from mathematical physics, introduced by Gabriel Lamé in the 19th century. So we have 6 new Lamé functions. There's Lamé C, there's Lamé S, and then there are associated functions, the derivatives and the eigenvalues in 12.2. Now C stands for roughly sine, cosine, and S stands for sine, and the question is why? Well, here's the differential equation for Lamé functions. So it's a differential equation with elliptic coefficients. So now these elliptic functions appear as coefficients of differential equations, and that's the corresponding eigenvalue. So you're solving an eigenvalue problem, and you get back Lamé S, in this case, as a solution. Now, although they look frighteningly difficult, these Lamé functions in fact have the trig functions as special cases, so you can boil them down to cosine and sine if you work a little bit. And that's because the parameters of the way can be adjusted to get you the differential equations for sine and cosine. So those are the first 3 even Lamé S function. They look almost like the sine function. They pass through 0. Okay. So the question is, why are they useful? Well, they are useful because they can be used to solve the Helmholtz equation in so-called spheroconal coordinates. That's a kind of elliptic coordinate system which is used quite a lot. So Lamé functions are new in 12.2, and that closes one more chapter of the famous book by Abramowitz and Stegun. And really, the question might be, suppose I have a special function which is only defined by a differential equation. It doesn't fit into the mathematical system. What do we do? Well, we have an answer for you, and we've had it for quite some time. That's the notion of a holonomic function. And of course, we have a holonomic sequence, then that's a special sequence. So we have differential root and difference root, which have been around since version 7, actually, and they have been quite useful, but we'd like to give them a new look. And so in version 12.2, they have new typesetting, they look nicer, they have better documentation, they're easier to use, and better numerical performance, etc. So here's a differential equation. You can set up any differential equation of your choice, linear differential equation with polynomial coefficients, and you can define a differential root object. You can plot it just like your own function. See, the nice typesetting over there hides all the details, but then you can drill in and actually work out what the details are. So differential root encodes all the information required to work with that special function which you just define yourself with without any kind of effort. Okay, once you've done that, you can compute the asymptotics, you can work with it inside all kinds of solvers, and it's just one more special function. So this greatly enlarges the scope both for our special functions and special sequences. So if you go to the book and you find that I don't have a function in Mathematica, well, you can define your own, okay? So we really hope that these functions will play a much bigger role in calculus in the near future. And there's a very nice talk by Tigran, which is planned today, which I hope you'll understand, attend to actually understand this whole area really well. Okay, so I now move on to calculus, and we have always had this Laplace transform function, first in package form, then a system function in version 4.0, and the Laplace transform is simply defined by an integral. So that's the integral that defines the Laplace transform. And the question is, what's the property of this integral? Well, the S over here is a parameter, and this integral is an analytic function of S in a complex half plane. So as long as you stay on the right of a certain vertical line, you're just fine. So that's a sawtooth wave, looks pretty messy, but its Laplace transform is nice and simple. And the question is, how do you go back from that formula over here to the sawtooth wave? And that's the hard problem with Laplace transforms, inverting them. So in version 12.2, we have the inversion of such transform using the Bromwich contour integral method. That's a famous method. The idea is that if you look at this function s of s over here, and you think of s as being a complex number, it has not just one, but infinitely many singularities. So you count them all up, lay them out in a sum, and you get back the original function. That's a hard problem. It was solved last year. And we also support for numerical inversion using numerics to do inverse Laplace transforms. And one last thing, we definitely wanted to give people better documentation. So we've done that over here, and actually we have wonderful documentation of Laplace and inverse Laplace transform in version 12.2. So I think that this is a kind of complete refresh for Laplace transforms. And just to give you a couple of examples for the inversion. So here is an example of a function which you found by Laplace transforming. And the question, how do you go back? Well, when you go back, what we do is we analyze all the singularities over here, and there are lots of them, and we sum them all up in an inactive sum. If you like it, you can activate it, or you can simply work with the inactive sum. You can plot it, and you see you get back this beautiful step function over here. So the documentation has got many more hairy examples for this kind of inversion Laplace transform, but I think this is a major breakthrough for us because it finally lets us go beyond the case of rational functions and other simple table lookup kind of things. And on the other hand, we also have numerical inversion. So there's a small community within our own which talks about numerical inversion quite a lot. And so we have numerical inversion of Laplace transform in Mathematica in 12.2. So here's a function defined purely numerically. The variable t is not allowed to be a symbol, and you can work out its inverse Laplace transform for this function at each point, like in 1.3 over here. Now, when we cooked up this example, we were quite proud of it because it did not give an answer in 12.1 symbolically. Well, due to our own efforts, it now works symbolically as well. So now you can compare the symbolic and numeric values, and you can actually use different methods. You can use method Durbin, Weeks, Talbot, Stayfest, whatever you like. You can, have a feast of methods available to you for your use for numerical inversion. And so here's a plotted function, nice and oscillatory, but now done purely numerically. So you can do symbolic inversion, you can do numeric inversion, and together you have a pretty powerful implementation of Laplace transforms in version 12.2. Okay, so let me now go on to a traditional area, differential equations, and we'll continue to break through for differential equations in 12.2. We have lots of improvements for exact solutions of linear and nonlinear differential equations. And here is, for example, the Hoyne equation, which we introduced in 12.1, the Hoyne functions, and that's the kind of normal form. It is a missing second derivative, first derivative, sorry, and that's the coefficient over here, and we get back an answer in terms of Hoyne t. So these normal forms hold the key to solving the general Hoyne ODEs, and we have cracked that problem very nicely using residue calculus, etc. So that's a big achievement, and in fact, we have been working so hard on DSolve that I believe, in some sense, we are now better than Maple for a large benchmark of problems. So so we actually have finally come to a point where we feel that we've done enough over here. We need to go on to other greener pastures. So two directions. We'll be first of all moving into the field of systems of ODEs for dynamic systems, etc. And we also want to record a course. So when I have a bit of free time after a month, I'm going to start recording a course on differential equations to teach everyone what differential equations are and how we can work in the system with them. But I'm really pleased with this achievement. It's a lot of hard work, and it's a great landmark for us. Okay, so going on to partial differential equations. Well, Unal gave a wonderful talk this morning, a very scholarly talk, and I hope you were there as well. But basically, we have lots of improvements for exact solutions. So here's the heat equation in genuine cylindrical coordinates. You got R, Z, and T. There's no theta over here, but you can get these beautiful plots of the heat evolution in time with our solutions. So I think we've come to a point where really there are cases where the numerical method might not actually give us such good answers as the symbolic one. Okay, and as Unal mentioned, we have a monograph in preparation, which will help people learn PDs from our point of view in version 12.2, just after maybe. It's a big project, hopefully finish it soon, but I think that at some point very soon, you will have your own mini textbook on PDs inside the system. Okay, so I think that this is a great improvement, and I think there's an environment of textbooks that are coming out for in this area, which is what we're trying to kind of cater to. Okay, now a little bit of asymptotics. So I worked in asymptotics for a couple of years along with the team, and a long time ago I worked on statistics. That is one of my, I would say, one of the most successful projects, and I did the initial implementation of probability and expectation in version 8.0. So I know asymptotics, I know probability. Can I put them together? Well, we've done that this summer, and we have two new functions: asymptotic probability, asymptotic expectation, which hopefully have some kind of use for asymptotic statistics, the study of limiting distributions which appear in all kinds of practical applications. So, the asymptotics really began with the publication of, Doctrine of Chances by de Moivre in 1738, and we actually have tried to give an example over here which shows that if you have the binomial normal and you put n equal to 30, let's say, and p is sufficient close to half, then the NGS, the moment generating functions, looks sufficiently simple. That's a nice intuitive way of understanding how the binomials relate to the normal distribution. So I think this will give a lot of insight, and it's a nice way to put back asymptotics and expectation and probability together in one frame. Okay, so that's about the asymptotics, and I'm quite happy that we're having this development over here. So let me go on to algebra now, and we have assumptions solved. That's a big break because we have always wanted them. Stephen Wolfram finally convinced Adam that yes, put them in, and we did. So here's an equation: x squared equal to a. X is a real number, and if you say a greater than 0, then of course you get back two solutions. If you say s less than 0, you get back no solutions. The problem is that when you talk about solve, the variable x is a global variable. So there's no parameter and variable separation over here. So here's an equation where you got solve 2 raised to x equal to 8. And in fact, if you put assumptions over here, that's no different from putting them inside the system. So assumptions are important solve, but they must be used with some understanding and care. But nonetheless, we have this wonderful option of assumptions for solve in version 12.2. We also have a lot of optimization coming in, which will be a separate talk by Adam Stresbonsky. He's a real expert, so I'm going to leave that to him to talk about later today. Okay, so just a few things more, and let's talk about linear algebra. So I think linear algebra is probably the most useful part of our area of Mathematica, and I think that we have tried to show it quite nicely in the recent linear algebra MOOC, which was released in August 2020. I was quite pleased with the response to the blog post. We getting lots of hits to the website, and in fact, people are finding there was just one typo in the whole course. 3 people found it. I'm really happy. I'm not happy with the typo. I'm happy that people found it. Okay, so I'm really happy people actually studying this course and learning linear algebra over here. We have a study group starting out next Monday, which I hope that some of you will consider attending. And we'll also have lots of new documentation for basic matrix functions, which has taken a lot of effort on part of the team in version 12.2. So linear algebra is now being refreshed. And one last area which I think is worth mentioning over here is polynomial algebra. So this is the kind of the oldest part of the system where we have, absolutely it's the heritage part of the city. It's the old part of the mathematics city. Okay, you touch anything over there, you might put yourself in real trouble. Okay, but we're going back over there. So here's the expand function, expands the polynomial, and we've worked on improved documentation for around 35. Expand, factor, etc. So these will get refreshed first, then we'll go on to the big leap of actually looking at the functionality itself. But polynomial algebra is another area where we're expanding out quite nicely. And just last month, I started a project to actually develop a course on introduction to elementary algebra, which will hopefully come out in the next year or so. So we'll have differential equations, and then after that, we're going to have the algebra course within a year or so. But I think it's important to teach young children how to do algebra by hand, and look at animations, do exercises, type in simple things, but they learn the Wolfram language, they learn algebra. I taught algebra for many years at middle and high school. I know how hard it is. It's much harder than doing anything else in the world. So this is the project which I really have in mind for the next year. Okay, so I think I should really finish up. I'm running out of time, but I just want to announce that our team is actually, going very strong, and we have lots of things today. This morning, Unal gave an excellent talk on symbolic PDs. That's my talk right now. You might want to go to Adam Stasbonsky's talk on optimization. He is truly an expert on this area, and you will definitely enjoy it and listening to his careful presentation. I'll have a meetup which I'll coordinate at 1 p.m. Do come along for that if you like mathematics education and want to discuss some ideas. It's a good chance to talk, not just listen to people like me and, in these talks. Tigran will give a talk on functions and properties at 2 o'clock. That should be a great talk as well. He's worked hard on first Hoyne functions 12.1, now Lamé, holonomic function properties he'll talk about. So this should be a very good talk for you to get an overview of what's happening in that area. And we have not one but two office hours. Itai will be coordinating those, and that's me and Adam will be helping out with those office hours. So do come along if you have any questions. If I didn't get to your question right now in the talk, if you've got some comments to offer to me, I'll be very happy to offer them. Okay, so I'm really happy with the way things are. Thanks to Roger, thanks to the team. We're a very loyal, dedicated, hardworking team. We meet every day. COVID has not stopped us. We have worked harder than ever. And it's great to see so much spirit in such difficult times. And I thank you very much, of course, for coming to the talk. And do give me your feedback. There's some time for questions, maybe a few minutes at least. So, I'm happy to answer questions now. I'm happy to answer questions later on. But, and in fact, Braden, who's coordinating, kindly offered to unmute anyone who wants to ask a question. So maybe it's a good point for me to stop and take a few questions. There's just one question which I noticed from Michael about n inverse Laplace. It's a good question, Michael. A couple of things. One is that we could have done that, and we probably will in the future. One thing is that we really want to return a kind of parametric function object, because the last argument of inverse Laplace transform is really a parameter. And so you want something that's useful on the whole range. So I hope that we can do that in the future. But Michael, I think I'll come back to you and find out what's on your mind. I totally agree with you. I would have loved to have it. By the way, internally, we are calling a function called transforms backtick n inverse Laplace transform. So it's there. If you can push us enough, we'll push it out into the system. I hope that answers the question. Any other questions for me? Right, so John asked about improvements for green functions. I think I'll come back to John. I think Unal is a good person to do that. Unal is here in the talk. I'll ask him to make a mental note of that. And that's one of my favorite functions. I just haven't had time to go back to it. Sure, John, we'll do that for you in the near future. Any other questions? Do type in or talk, whatever. We have a couple of minutes, and then I'll stop and but I do appreciate all your positive response, your support of this old but interesting area. So if there are any questions, please go ahead. We have a minute or more, and then we stop. Okay, thank you very much. It's 10:30, and I think I should let you go. And I really do appreciate all your effort for the next release, or the team and users who are actually keeping us going. So thank you very much. I'll stop over here.